Welcome to this session on Evolving for Performance with OpenEdge 12. My name is Dan Mitchell. In this session, we're going to dive into the enhancements in OE12 that we believe will provide you with some pretty significant performance improvements. Over the years, our mission hasn't changed. We've improved OpenEdge to keep up with ever-changing requirements and continue to surround it with products that help keep your OpenEdge-built application modern and relevant. One of the major focuses of OE12 was around improvements in performance and scale. This session is going to highlight the key performance enhancements that are coming in this release that is due out at the end of February. So what have we done with OpenEdge 12? In this session, we're going to discuss 4 changes that have been made that will help you not only get more life out of your existing application, but will help you to evolve your app to address tomorrow's scale and requirements. In OpenEdge 12, significant effort was put into improving overall performance of the OpenEdge database. To help extend your existing applications, we have improved performance around shared memory, which up to now has been the best way to make your application perform. To scale beyond the confines of shared memory, we've added 2 new features to OE12, which will improve performance when the database is accessed from remote clients instead of through shared memory. All of this without making any changes to your application code. We're going to use a visual representation to help you see the increases in performance. We'll show you a video of the Space Shuttle launching. In the left pane, you'll see the Space Shuttle launching using 11.7. In the right pane, you'll see the same launch with the performance enhancements we saw during our testing for version 12. The speed of the launch represents transactions being processed. So, right out of the box, we made some pretty significant improvements to performance. We're addressing the shared memory as a single point of failure and also how it can limit scalability. Many existing applications written with ABL connect to the database in a self-service mode through shared memory. In the past, this was the best way to maximize performance. As applications evolved into client-server models, the clients were disconnected from direct database access and were moved to app server connections. In order to help the performance of app servers, many folks put the app servers on the same machine as the database and connected them as self-service clients using shared memory. In this model, self-service presents a potential bottleneck and a risk for the application. Any client or app server connected as a self-service client can cause the database to crash and recover if they incorrectly terminate. There's a very remote chance that this can happen. Many of you may not have ever even experienced it. If you can move the app servers to a different machine, you can access shared memory through a remote connection, and you can eliminate this possibility. So, our ultimate goal is to improve scalability and availability by providing performance for remote clients that is equal to self-service. As part of our work to improve the overall scalability of the OpenEdge database, we're working to optimize access to shared memory. Your applications today may continue to use self-service connections because, as we have seen, the use of shared memory provides great performance. When developing version 12, our first step was to determine where contention takes place today, and the buffer hash table was isolated as one contributor to performance degradation. Hashing is a key technique to store and locate records in the database, and latching is required to ensure that everything works properly. Latching can lead to delays when a specific buffer hash table area is latched when someone else wants to access it. Improvements here can lead to performance gains. As hardware has evolved from 32 to 64-bit, there is significantly more RAM available for use by our buffer pool. Users are creating larger and larger pools using the Big B parameter to assign more memory to the buffer pool. Increasing the Big B creates more buffers that need to be managed by the server. This is done by something called the buffer hash table. When we reviewed how we were managing this, we found a bottleneck in the latching mechanism that controls access. When memory models were smaller, a fixed number of latches could handle the load. But as memory grew much larger, we found that we needed to dynamically allocate more latches based on how big the buffer pool is. Additionally, OpenEdge 12 has greatly decreased the need to use the buffer hash table for certain sequential index searches, again improving access to the buffer pool. When a record is retrieved as part of a sequential read, as in a for each statement, the behavior has been changed so that when the record is retrieved, the next record in the sequence is noted. Because of the sequential nature of the query, it's likely that the next record is still in the buffer. This means that finding the next record will not require a buffer hash table latch. In the past, this was not done because it was thought that the next record could have potentially been flushed from the buffer pool, so it needed to be hashed. With larger Big B settings, this is generally not the case, so the behavior was changed. Buffer hash table latching improvements yielded a 28% improvement in overall performance in our internal testing. Now you can see that the shuttle gets off the pad much more quickly. Another potential bottleneck is how client requests to the OpenEdge database are processed. Today the processing is serial, one request at a time. This works reasonably well if there is no record contention. But as soon as a request needs to access or change a record that is currently locked by a different client, that request is sent to the back of the queue and waits until it gets another turn to be processed. If in the meantime the record lock is resolved, the client cannot proceed with processing until it gets its turn with the database server. You might be saying, I thought the OpenEdge database is already multi-threaded. Well, you're absolutely correct. The storage engine is multi-threaded, PassOE is multi-threaded, the SQL engine is multi-threaded, and many of the database utilities are as well. The issue is that the actual ABL's database server is not. This means that requests from multiple remote clients are handled one at a time. Here's a picture that shows how server requests have been handled up through 11.7. You can see that the messages for the database all report to one server process. It spends a lot of time controlling traffic. In the new model, the server process is only required to manage parallel requests to the data. This is a much more efficient model because the server process is no longer a limiting factor. So adding multi-threading to the database server provides us with several benefits. Improved performance because multiple requests can be sent simultaneously, so there isn't any waiting. We spend a lot of energy on how to handle waiting requests, spins, naps, things like that, and this can be greatly reduced. Remote clients will be faster, so they don't have to connect directly to shared memory. This creates better availability because killing of a remote client won't crash the database. This was also a requirement to enable our server-side join project, which I'll discuss next. Adding multi-threading to our visualization gives you an idea of the benefit we found in our testing. Finally, we're improving how query processing takes place. Today, when a query involves multiple tables, a series of communications between the client and the database server take place, and typically a superset of records is returned to the client, who in turn carries out the join operation to produce the desired result set. The number of additional unneeded records sent to the client can be high, which takes up bandwidth and time to transmit needlessly. The improvement is to resolve as many queries as possible on the database server, so that the final result set is returned to the client. In OpenEdge 12, we realized our goal of releasing server-side joins without requiring any application code changes. In the first release, it will work for each statements that access up to 10 tables. It does require that you enable the multi-threaded database server. And we've added a number of new logging facilities to help you understand the impact of server-side joins. Why do server-side joins matter? Well, we found that having to filter less records on the client side improved client performance. Also, since we're sending and receiving less messages between the client and the server, there is a reduction in costly TCP/IO operations. In version 12, this feature is only available for each static queries that are no lock. The query also can't involve mem pointers, and it supports a maximum of 10 tables in the join. Additional functionality will become available in subsequent releases. Our engineering team did a number of benchmarks to help us understand what the benefits of server-side joins would be. This chart highlights the results. The query they used was as you see here in the blue box. You can see that the number of database reads was reduced by 25%, and the number of records sent from the server was 62% less. You can also see that network traffic was reduced by orders of magnitude for this sample query. 5 times fewer messages sent, 7 times fewer messages received, 5 times less data sent, 11 times less data received, 2.5 times less data sent, and 5.5 times fewer query requests. So to complete our visualization, this is how the shuttle would launch with all of the OE12 enhancements enabled. You can see that the 11.7 shuttle is still on the pad, while the 12.0 shuttle is nearly in outer space. Up to 3 times improvement versus 11.7 in n-tiered deployments. Of course, as always, your mileage may vary depending on your architecture and use case, but we encourage you to try running your app in OpenEdge 12 to see what kind of results you will see. You can see much better performance if you see the same results that we did in our tests. So, how will this influence your application evolution? Progress has historically recommended that the application and database use shared memory to maximize performance. This requires the application server and the database to reside on the same server. With the performance improvements shown in this presentation, we find the performance of remote clients and application servers now approaching the performance of self-service applications. Version 12 will continue to improve remote client connection performance to the point where it will eventually match shared memory performance. Remote connection removes the risk of shutting down the database server because of a shared memory disconnect. It also improves the scalability of your application because it gives you the ability to add additional app servers as needed. Progress OpenEdge 12, coming at the end of February. Get ready.